In our previous video, we implemented DMVPNs. In this video, we're going to overlay on top of that the protection of IPsec for confidentiality. Let's begin. There's a couple of really great benefits of setting up DMVPN before we add the IPsec on top of it. Number one, if we want to do packet analysis, we can actually see what the heck is really going on in those packets because they won't all be protected by IPsec. So we can dig into the details of the NHRP requests and replies, and the actual packets that are going back and forth and see their contents. The second benefit is for the benefit of troubleshooting. If there's a problem with DMVPNs, we want to identify that well before we put on the IPsec. Because the IPsec and the keys involved in the transform sets adds a whole nother level of possibilities of why it might not work. So in a lab environment, especially as you're learning this, I would strongly encourage baby steps. DMVPN first, and then adding the IPsec on top of it. So our existing network, as we left it in our previous video, is working with DMVPN. And let's bring out a protocol analyzer, and let's take a look at some ping traffic between R2 and R4. Now initially, the packets would go to the hub, it'd be sent over here. But once the NHRP resolution's been done for that GRE next hop of R4, then the packet should be able to go back and forth. And because we don't yet have IPsec on top of it, we could do a protocol analysis and see the details of that traffic. Now let's have some fun with this. When we left our network last, we saved the config and I brought it back up this morning. And just to verify it's still in good shape, R2 should see the next hop to get to 10.4.4.0. It should see the next hop is 172.16.0.4, which is the tunnel interface of R4. So let's verify that with a show IP route for EIGRP learned routes. And sure enough, there's the 10.4.4 network. The next hop is 172.16.0.4, which is the GRE tunnel interface of R4. And our egress interface from R2's perspective would be our tunnel interface. So if we try to forward traffic to 10.4.4 anything, that's going to trigger the NHRP request. So we can learn the NBMA address and then start forwarding traffic after we know that IP address back and forth over GRE between R2 and R4. Now the question is, does R2 already know that mapping, yes or no? We can find out with the command show IP NHRP, and that'll show us all the mappings that R2 currently has. So at the moment, R2 only knows about the IP address 172.16.0.1, which is the tunnel interface of the hub, and the interface address of the hub is 15.0.0.1. Another really cool command I'd like to share with you is show DMVPN. That'll also give us a bird's eye view of what's going on from a DMVPN perspective. So here's the command, show DMVPN. And here we have the Dick Tracy decoder ring regarding attributes and status. For example, the attribute of S right here represents that it is a static mapping. Wasn't learned dynamically. Here's the NBMA address of our hub right there. The tunnel address of that device is the tunnel 0 interface. And it's been up for a few minutes. So I've got a question for you. What would we need to do on R2 to dynamically start learning additional NBMA addresses? For example, the NBMA address of 45.0.0.4, which is associated with 172.16.0.4. And if you're saying, Keith, all we have to do is send traffic down to 10.4.4.4, and because the next hop is this IP address, from the routing table perspective on R2, that would trigger the NHRP lookup. And you, my friend, would be absolutely right. So let's do that. Let's go ahead and do a ping from R2 down to 10.4.4.4. And what we'll also do, let's source this from our 10.2.2.2 address, which is local on R2. So we'll do our ping. Let's repeat it twice. And those pings made it. Now, it's very likely that the initial ping went through the hub this direction. But it's possible that the second ping and now future pings are going to go back and forth directly between R2 and R4 because in the background they did the NHRP resolution. So how could we verify that? Well, let's use the up arrow key a couple times. Let's do a show DMVPN, and let's take a look at the table to see if it's any bigger. So now the output of show DMVPN shows that we still have our static entry right here, but we also have two dynamic entries. This first dynamic entry, which has the NBMA address of 45.0.0.4, that's R4's interface address, is associated with the peer's tunnel address of 172.16.0.4. And the reason that's here is because we were actually sending a packet to the IP address of 10.4.4.4. This next entry is very similar, except it's simply describing the 172.16.0.4, which is the next hop, which has the same information. The tunnel address is 172.16.0.4, that's here on R4, and the NBMA address on R4 is 45.0.0.4. So now, in the lookup, whether we're looking for that IP address or that next hop, R2 knows that the NBMA address for either one of those is 45004. Another way of seeing that same information is with show IP NHRP. So there's the one for 10.4.4.4, and here's the one for 172.16.0.4. So this command, show IP NHRP or show DMVPN, are both great ways to see what's really going on regarding the dynamic mappings in DMVPN. Now, one last thing that I'd love to do is let's use the up arrow key a couple of times, and let's do a couple more pings between R2 and R4. Now, those were successful, and if we take a look at those in a protocol analyzer, which, by the way, I have because I set up a capture just a few moments ago, we can then look at the details of those packets that were exchanged between R2 and R4. I started this capture before we did our first commands on R2, and I was doing the capture on the link between R2 and the internet. So we have 493 packets that are captured. Now, to sort through some of this, what we could do is set up a display filter. And the full details for using Wireshark, you can go ahead and catch inside of the Wireshark course here at CBT Nuggets. But for now, let's go ahead and set up a couple simple filters to get rid of some of this noise. For example, if we want to get rid of the EIGRP hello messages, we can simply go to EIGRP, right-click on it, and say, I want to go ahead and apply as filter, and say not selected. That'll remove that from the current display. Next, we have all these self-tests that are being run by interfaces. And if we want to get rid of that, we simply select a packet, go down to the protocol, right-click on it, and say, I want to go ahead and apply as filter. And I'm going to say here, and not selected. So it's actually building this filter right up here for you. So if you want to, you can actually put the syntax here, or you can let the menus help you build that filter. Next, we have a whole bunch of, looks like CDP messages, sure enough. So if we don't want to see that, we can right-click and say apply as filter, and say and not selected. So with these display filters in place, we have 16 packets that are left, and most of them are related to NHRP, Next Hop Resolution Protocol, and some ICMP packets that were part of the ICMP echo and echo replies. So if we take a look at our very first ping here, which is packet 281, when you're looking at this, we want to be a little bit careful about this information right here. See, although it says it's going from 10.2.2.2 to 10.4.4.4, Wireshark pulled that out from the GRE encapsulated payload information. But upon closer inspection, if we look at the layer 3, the outermost IP header, this is a packet that's coming from R2 and going to R1. The very first ping was sent actually through the hub because NHRP resolution hadn't yet been done. And then inside that IP header, it indicates that the next protocol is generic routing encapsulation, which is protocol number 47. And then if we open up the GRE header, we have a hexadecimal representation of the key that was configured for both ends of the tunnel for both peers. In this case, the peering for this GRE tunnel is between R2 and the hub, which is R1. So what happens is when R1 receives this and starts de-encapsulating it, looks at the GRE header and says, okay, what's inside of this GRE header? And then looks at the GRE information and says, oh, the next protocol is hexadecimal 800, that's IP, specifically IP version 4. So then R1 would go ahead and open up the IP header information, look at the destination, and say, oh, 10.4.4.4. I know how to get there, and it re-encapsulates it and sends that packet out over to R4, who, after de-encapsulating the outside IP header and the GRE header, will identify, hey, this packet's for me. We also have, in packet 282, we have the NHRP request coming from R2. And then if we scroll down and we go down to our second set of pings, which is right here, because the resolution has already been done, like a couple hundred packets ago, now we can see that the outermost IP header is sourced from R2's NBMA address going to R4's NBMA address. Inside that outmost IP header, it indicates that the next protocol is GRE. If we take a look at the GRE header, it indicates that the next protocol is 800. And inside that, we have the original IP packet and payload that was being sent, which indeed is a ping packet source from 10.2.2.2 with a destination of 10.4.4.4. And if we open up the ICMP information, it indicates that it's an ICMP echo request, to which R4 in packet 462 will do an ICMP echo reply. And again, the benefit of doing the DMVPN before IPsec is overlaid on top of it is so that we can see the details of the payload. Because once we put IPsec on top of it, anything that IPsec has encrypted, we are not going to be able to easily see the contents and the payload of those packets once it's all encrypted with IPsec. And what I just did is I saved this file called dmvpnnaked.pcapng, and I've saved it as part of the Nugget Lab file. So if you want to go through this and take a look at those details, it's there as a reference. And another option, if we wanted to clear this display filter, I just want to look for NHRP. We can just type in NHRP, and that would show us just the NHRP traffic. If we wanted to look at just ICMP, we could say ICMP. Or we could do a filter that includes both ICMP and NHRP. Now our next piece is to add on top of this IPsec. So let's do a quick check with a show crypto ISACEMP policy and press enter just to see what policies we have in place. Now there is a boatload of default IKE Phase 1 policies on Cisco routers in iOS. And if you want to use those, that's great. However, it's oftentimes a lot better to control exactly which policies are going to be used by creating them manually. So what we're going to do is we're going to go into configuration mode and we're going to create crypto ISACEMP policy number 5. And from a priority perspective, the lower the number, the better the priority. Now you and I have already had some exposure in creating IKE Phase 1 policies in our CCNA security videos right here at CBT Nuggets. And inside of an IKE Phase 1 policy, there's 5 elements that we are going to negotiate with our peer. And the acronym that I like to use to remember those is haggle. We're going to haggle and negotiate regarding these parameters for the IKE Phase 1 tunnel. The H is for hash. The A is for authentication. And as a brief reminder, hashing is a great way to do data integrity checks. Authentication is a great way to validate the peer at the other side that you're talking with. The G is for the Diffie-Hellman group. And Diffie-Hellman is the algorithm that's run between two devices to negotiate and set up a set of shared secret keying material, or in simple terms, a shared key that can be used with symmetrical algorithms between those two devices. And there's a lot of flavors that we can use. For example, Diffie-Hellman group 1 or 2 or 5 or 14, and the list goes on. The L is for lifetime. How long do we want this IKE Phase 1 tunnel to stay up? And the E is for encryption. I'm just going to do the short version of it there. And the encryption is what gives us our confidentiality. That puts the private inside of virtual private networks. And so for that, we can use triple DES or AES. And with AES, there's several flavors. And that's all for IKE Phase 1. And any of those parameters that we don't specify, there are defaults that the system will assume that we want to use in the absence of specifying the detail. So in our policy for hashing, let's go ahead and do SHA. And for the authentication, let's take a look at our options by using a question mark. So we have pre-shared, which means we're going to go ahead and do a hard-coded pre-shared key on both peers, and that key needs to match. Or we can use RSA signatures, which implies we're going to exchange digital certificates with each other. Each of those digital certs has the other party's public key. We'll do some digital signing and verification on both ends for mutual authentication. And in our case, because I don't have a CA set up in this topology yet, let's go ahead and use a pre-shared key for authenticating both sides. So we'll type in pre-share, press enter. For the Diffie-Hellman group, we have lots of choices. Let's use a question mark. And I still remember when we thought that Diffie-Hellman group 5 was like the cat's meow. Whoa, Diffie-Hellman group 5. But now we've got like Diffie-Hellman group 14 and 15 and 16. And the bigger the number, the more bits are involved and the more secure that algorithm is considered. So for our example, let's go ahead and use 14. For the lifetime of this IKE Phase 1 tunnel, I'm going to put in the default of 86,400 seconds, which is just about 1 day's worth of time. And for the encryption, let's take a look at our options. So I'm going to use a question mark here. We've got triple DES, DES, and AES. DES, friends don't let friends run DES. And unless there's a burning reason to use triple DES, we probably want to avoid that as well. So let's use AES. And a question mark reveals that we have 3 flavors on this platform. We have 128, 192, 256. And again, in cryptography, bigger is better. The more bits involved for the algorithm, the more secure that algorithm is considered. So let's go ahead and use 256 and press enter. And then we can exit out of the crypto ISACEMP configuration mode. And again, you don't have to specify all those details, but if you don't, for example, specify the authentication you want to use, it can use the default authentication method. And if that happens to be RSA signatures and you don't have digital certs yet, that would be another reason why the IKE Phase 1 could fail. And IKE Phase 1 has to get going to build a communication path between the two peers so they can get to work and then build the second phase of IKE version 1, which is IKE Phase 2. And if you'd like a little refresher on the basics of cryptography, symmetrical versus asymmetrical, and how IPsec version 1 operates, I would strongly recommend that you go back and revisit 2 specific videos in the CCNA security course. And the titles of those videos are Cryptography Essentials, and the other one is called IPsec Site-to-Site VPNs. Because those 2 together will be a great refresher on a lot of these basics. Now, because we specified in our policy that we want to use pre-shared keys for the authentication of IKE Phase 1, we need to specify what those keys are. And to do that, we're going to use the command crypto ISACEMP key, the key we want to use. And in this case, I'm going to use the keyword address. And then I'm going to do something that you probably should not do in a production environment. I'm going to specify wildcard, which means anybody who has this key of Cisco 123, I'll be happy to go ahead and peer with them. And you know what? I'm going to hit the up arrow key and do a no in front of that because of what I did right there. I put a space right there. And whenever we're putting in passwords or codes, a lot of times they'll accept a space either at the middle or at the end of a syntax. So in the event that this thinks that the space at the end is valid, I don't want to make the mistake of configuring it without a space at the other locations. For example, R2, R3, and R4. Because then if the key doesn't match, the IKE Phase 1 authentication is going to fail, and we're not going to get too far. So I'm going to hit the up arrow key a couple more times and go back and remove the additional space, just to play it safe. Next, let's create a transform set. And the transform set simply specifies for IKE Phase 2 exactly what do we want to use, what kind of encryption, what kind of hashing. So the syntax is crypto IPsec transform-set, and I'm going to call this one our set, yours and mine. And if you use the question mark to take a look at the options, we have lots of options. So we're going to say ESP dash, referring to encapsulating security payload, which is protocol number 50, which is the main protocol we're going to use with IPsec. And let's go ahead and use AES. And then if we put a space, we also have flavors of AES that we can use here. We don't have to use the same exact flavor of encryption for IKE Phase 2 as we do for IKE Phase 1. Those two phases with IKE version 1, those are two separate tunnels. So let's go for 256. We can also tag onto this transform set the hashed message authentication code that we want to use, which is very much like a hash, but we're including in the mix some keying material so that anyone who's eavesdropping can't recreate that hash if they don't have that keying material. So if you do a question mark again, let's use ESP-SHA HMAC. So great, there's our transform set called our set. Now you'll notice it put us into transform set configuration mode. So in this transform set configuration mode, we'll simply say mode space transport. The default mode is tunnel, but in this case, because the packets really are going between the interface addresses between R2 and R1 or R2 and R4, we don't need to hide those IP addresses behind IPsec just to replace them with the same IP addresses. So in this case, we're going to use transport mode, which leaves the original IP addresses intact. Next, we're going to create an IPsec profile that we can apply to the tunnel interface here on R1. The syntax for creating this IPsec profile is crypto IPsec profile, and then we're simply going to name it. Let's call this one our underscore IPsec underscore profile. And that puts us into profile configuration mode. And what we're going to do is we're going to tuck this beautiful transform set that we just made right here. That for IKE Phase 2 is going to use AES 256 and SHA HMAC. And let's go ahead and tell this IPsec profile that we want it to use for IKE Phase 2, that transform set. Now in our traditional IPsec site-to-site tunnels that we set up in the past, we'd use a crypto map, and then inside the crypto map, we would specify the transform set. Here, we're simply associating the transform set with the IPsec profile. So to do that, we're using the command set space transform-set, and then the name of our transform set, which was called our set. And let's go ahead and get out of crypto IPsec profile configuration mode. Now our last step is to apply that IPsec profile to the tunnel interface. So we'll go into interface tunnel 0. We'll say tunnel protection IPsec profile, the name of our profile, and press enter. So in this case, our profile is called our underscore IPsec underscore profile, and now it's applied to that tunnel interface. Then we're going to have periodic messages that are being sent to R1. Coming in from R2 and R3 and R4, for example, if one of these registers or does some kind of a keep alive with NHRP, that traffic is not going to be encrypted. However, the tunnel interface on R1 is going to be expecting that data to be encrypted. So there's an example. It says, whoa, I just got a packet. It was destined to 15001. It was sourced from 25002. It's protocol 47, which as we know is GRE. And it's not IPsec. It should be. I'm not accepting it because it should be encrypted. So what we need to do to correct that is we need to go to R2, R3, and R4. We need to create compatible IKE Phase 1 policies. We need to create compatible transform sets. We need to associate those transform sets with an IPsec profile and apply those profiles to the tunnel interfaces of R2, R3, and R4. And on R2, we're going to do virtually the same thing again. We're going to create our IKE Phase 1 policy. Let's go ahead and call it Crypto IceCamp Policy number 5. Hashing SHA, authentication pre-share, Diffie-Hellman group 14, a lifetime of 1 day, and encryption using AES 256 for the IKE Phase 1 policy. And again, the policy number itself doesn't have to match, but there does need to be compatible policies between the two devices. And although the two devices are willing to fudge a little bit on lifetime, they can accept the lower of those two values, all the other parameters in the IKE Phase 1 policy, they need to agree 100% with each other for the IKE Phase 1 tunnel to succeed. Next, let's go ahead and specify the key we want to use. We'll do Crypto IceCamp key, Cisco123, address 0.0.0.0. Now normally what we would do is we'd put in the literal address of the host that we're going to go ahead and use this key with. So in a lab environment, we can use the wildcard of all zeros, but in a production environment, you're very likely either going to use RSA signatures with digital certificates for authentication, so you don't have to worry about the key, or you're going to have specific IP addresses of the peers that you expect to be peering with. So in the case of R2, if we wanted to put in manual keys for each host, we'd have one for the host at 15.0.0.1, one for R4 at 45.0.0.4, and one for R3 at 35.0.0.3. And the rub is, if these really are dynamically assigned IP addresses on the spokes, and they change from time to time, having a manual entry for a key for those devices isn't really manageable, because once the IP address changes of one of those peers, we'll no longer have a key associated with that IP address. And that's why in a large environment, instead of using a pre-shared key, we'd very likely use digital certificates, where we could go ahead and authenticate a device using RSA signatures instead of pre-shared keys. Next, let's go ahead and create our transform set. We'll call it our set with the same transforms that we used over on R1, including AES 256 and SHA HMAC, and we'll specify the mode of transport for that transform set, and then we'll exit out of transform set configuration mode. Next, we'll create our IPsec profile. We'll call it the same name we did over on R1. It doesn't have to be the same name. However, it does have to have a transform inside of it that is going to match the parameters over on R1. In this case, I'm just mirroring the configs. And our last step is to apply that IPsec profile to interface tunnel 0. So inside interface config, tunnel protection IPsec profile, and the name of our IPsec profile. I'm also going to go into interface gig 1/0 and simply shut down that interface. I'm going to do that also on R3 and R4 so I can bring them all up at once and we can see the activity. So to finish this up, we need to bring up the interface of gig 1/0. So let's do that here on R2 with a no shutdown. And we'll do the same thing on R3 with a no shutdown for that gig 1/0. And the same exact treatment for R4, which I also left in a shutdown state after I applied the same IPsec configuration to it as I did for R2 and R3. So now they're all up, what should be happening is the GRE traffic should all be encrypted, and if it's working correctly, we should have EIGRP neighborships being established once again with R1. Another way of verifying that it's all working is we could go back up to R2 and just see what R2 has regarding EIGRP routes. So if the encryption is all working, R4 is sharing his route up with R1, R1 sharing the 10.4.4 network with R2, that should show up in the routing table of R2. So over on R2, let's do a show IP route, and that should give us the entire routing table, and I do see some EIGRP routes there. Let's use the up arrow key, add on the keyword of EIGRP, and that will show us just the EIGRP learned routes. Sure enough, there's the 10.4.4 network with the next hop of 162.16.0.4. If we want to verify whether or not the NHRP resolution has taken place, we can do a show IP NHRP. And because I shut down the interfaces, all the dynamically learned mappings are gone. However, to bring them back, we can just do a ping. Let's do a ping to 10.4.4.4. We'll just do a repeat count of 1. And then we can use the up arrow key a couple times, do a show IP NHRP. And sure enough, now we have a mapping for that next hop to the NBMA address of 45.0.0.4. And if we did another ping, and then did a show DMVPN, and a show DMVPN can help us verify our current peers that are in place. So this I right here represents incomplete. Let's do a couple more pings. Let's do another ping to 10.4.4.4. We'll source this from 10.2.2.2. That should force the NHRP resolution on both sides to happen, because R4 will also want to resolve, hey, how do I get to that next hop which is the tunnel interface of R2 to get back to the 10.2.2 subnet. And let's also do that with 10.3.3. So a ping to 10.3.3.3, sourcing it from our 10.2.2.2, repeat count of 1. And now with that, let's use the up arrow key a couple times, use show DMVPN, and we no longer have any incomplete entries. And the most important part of this is the mapping of the next hop address to the NBMA address for R4, and the next hop address and the NBMA address for R3. Another really cool option we have with show DMVPN is the option of adding the keyword detail to the end of it. And that will show us the same information as before, but it also gives us individual detail on the security associations from an IPsec perspective that are happening with those peers. So regarding our session between us, 25002 on UDP port 500 and the remote 35003 on UDP port 500, that represents our IKE phase 1 traffic, which uses UDP port 500. And then we go down to the IPsec information, which represents IKE phase 2 in IKE version 1. Here we have inbound packets decrypted, outbound packets encrypted. Any drops, looks like we did have one drop. That may have been when it was first setting up. And as we scroll down further, this has our information about the security associations we have between us and 45004, which is R4. So here's the IKE phase 1 information and the IKE phase 2 information regarding packets encrypted, decrypted, and so forth. What's also cool is that our normal IPsec related commands are still available. For example, we can do a show crypto ISAKEMP SA to take a look at the IKE phase 1 sessions that we currently have in place. Now, we do not need more than one IKE phase 1 tunnel between R2 and the other 3 devices in this topology. And they all have different connection IDs, which appears that all these are valid IKE phase 1 tunnels. And that could have been they both started trying to build the connections at the same time. Another favorite command of mine is show crypto ISAKEMP SA and adding on the back of it the keyword detail. So this includes information regarding that IKE phase 1 tunnel regarding the encryption being used, the hashing, the authentication method, the Diffie-Hellman, and the lifetime that's remaining on those tunnels. So if we scroll down just a little bit, so this guy right here and this one right here are redundant. And so are these two right here. So because the timestamps are identical, it would appear that when both those sites, like R2 and R4, and R2 and R3, when they did that next hop resolution protocol, when they did their resolution through the NHRP, they both immediately tried to build IKE phase 1 tunnels with each other. And that's why we have 2 sets. When in reality, we only need 1. If we wanted to see the details regarding a specific security association with a peer, we'd use the command show crypto IPsec SA peer. In this case, let's use 45004. And this will give us all the details regarding our security associations from an IPsec perspective between us, R2, and R4. So here's the command we used. And what this says is any traffic from me, which is 25002, that happens to be GRE, which is protocol 47, I'm going to go ahead and encrypt. And on the other side, router 4 at IP address 45004 is playing the same game. So any GRE traffic back and forth between those 2 peers using these IP addresses are expecting encrypted GRE traffic. So to verify that, I've just started up another capture to capture the traffic on this link between R2 and the internet. And with that in place, let's go ahead and do a ping. We'll ping to 10.4.4. We'll source it from our 10.2.2 network address, and then we'll say let's repeat 1 time. And because the NHRP resolution had already been done, that should have been trafficked directly between R2 and R4. So now let's take a look at the capture. Unfortunately, most of this traffic is all protected because it was all GRE traffic going back and forth, and every GRE packet going between R1 and R2 or R2 and R4, it's all going to be encrypted. So we can't really look for ICMP as a display filter because the protocol analyzer doesn't have any clue about the encrypted details in the payloads. So what we can look at is we can look for the source address of 25002 going to the destination address of R4. And I think this is it right here. So the IP header says it's going from 25002, destination is 45004. Inside the IP header, it says the next protocol is 50, which is ESP. And ESP says, I've got a little bit of information. For example, the security parameter index, which is the one ending in AD27. That was in the ESP header. But beyond that, all the rest of that payload is encrypted. We don't know if it was pings or GRE traffic or pings inside of GRE. We have no idea. It's all encrypted. So to validate some of that, if we take a look at that SPI number that ends in AD27, so if we go back to the command line interface on R2, and we issue the command show DMVPN peer and specify we want to look for traffic regarding the NBMA address of 45004 with the keyword detail, and I'll go back up here and show you that command once again. So here's the command that says show me all the detail regarding the peer who has the NBMA address of 45004. This is showing the tunnel interface that's being used, the current status of that interface, the IPsec profile that's being applied, and if we scroll down a little bit, here it has the outbound security parameter index that's being used for all outbound traffic that's being sent from R2 to R4 over the IPsec tunnel. And that does happen to match the SPI right here that we see in the trace. And in troubleshooting IKE version 1, which has IKE phase 1 and IKE phase 2 in it, we'd want to make sure that IKE phase 1 is working and successful. And then after that, we could worry about IKE phase 2 in that order. Because if IKE phase 1 isn't successful, IKE phase 2 cannot be negotiated and set up. Some debugs we could use to help troubleshoot that. If we're looking specifically at IKE phase 1, we could use debug, crypto, isokemp. So if phase 1 comes up and it's working, we're now trying to troubleshoot phase 2, which is the actual IPsec security associations. We could do a debug, crypto, IPsec. So phase 1 and phase 2. But since it's working, and we have traffic that's being encrypted and decrypted respectively, it looks like our IPsec is in really good shape. And you'll notice our DMVPN, the functionality still works the same, except now we have the protection of IPsec on top of it. So I've got some great news for you. All of the commands that I've issued in this video that we've gone through together, I've included as part of the Nugget Lab files. I'm also including the packet captures of the before and after regarding IPsec on our DMVPN, so you can have those as a reference as well. I have had a great time in this video, and I'm so glad you joined me for it. There's a couple of action items that are really important. Number one, I would strongly encourage you to lab up everything that we've done in this video. That includes the DMVPN portion from the previous video and the IPsec portion from this video. So if you have a test lab with live gear, or if you have a GNS3 environment that you can play with, either one of those will be great. The other thing I'd strongly recommend is that you review 2 videos from CCNA Security, specifically the one called Cryptography Essentials, and the other one called IPsec Site-to-Site VPNs, because that'll help refresh your memory regarding the basic concepts of cryptography, including the details of how IKE version 1 operates with its phase 1 and phase 2. And that's it. So again, thanks for joining me. I hope this has been informative for you, and I'd like to thank you for viewing.